On July 4, 2012, 10,000 physicists opened champagne. CERN had found the Higgs boson, the last missing piece of the Standard Model, the most precisely tested theory in the history of science, had been confirmed real. Front pages ran it worldwide. Fabiola Gianotti stood at the podium and presented the data, and in the audience, Peter Higgs, the 83-year-old theorist who had predicted this particle half a century earlier, sat with tears forming in his eyes. He would later say it was an incredible thing that it happened in his lifetime. The celebrations lasted for months. Nobel Prizes were awarded. And buried inside the data, in a number that almost nobody outside of a handful of theoretical physicists wanted to discuss publicly, was a crack. Not a metaphorical crack. Not a poetic way of saying something was slightly off. A literal instability in the fabric of reality, written into the mass of the particle they had just discovered. The Higgs boson came in at 125.2 giga-electron-volts. That number was not a surprise because it was wrong. It was a surprise because of what it meant when you plugged it into the equations that govern the vacuum of space. The vacuum, the empty space that everything in the universe sits on, that you are sitting in right now, is not the lowest energy state available to the laws of physics. It is a ledge, a local minimum on an energy curve that, if you follow it far enough, drops into something deeper, something fundamentally different from the universe you know. This was not a fringe interpretation. Within months of the Higgs mass measurement, a team led by Giuseppe Di Grassi, Stefano Di Vita, and 7 other physicists published a landmark calculation at next to leading order, the most precise computation possible at the time, and the result was unambiguous. For a Higgs mass below 126 GeV, absolute vacuum stability is excluded at 98% confidence. The quartic self-coupling of the Higgs field, a number called lambda that governs the shape of the energy potential, turns negative at around 10 to the 10 to 10 to the 11 GeV. When lambda goes negative, the potential curves downward into a second, deeper valley, a true vacuum. And the state we inhabit, the state that allows atoms and chemistry and stars and brains, is the false one. You were never told this. You were told the Higgs boson confirmed the Standard Model. You were told it was a triumph. And it was. But the triumph carried a confession that the institution celebrating it chose not to put in the press release. The particle they found does not describe a stable universe. It describes a universe perched on a shelf, held there by quantum mechanical inertia, surrounded by a void that the math says is temporary. Peter Higgs himself was an unusual man to be at the center of this. He never used email, never browsed the internet, never owned a mobile phone. His Oxford colleague Frank Close titled his biography Elusive, and it was not just a reference to the particle. Higgs published fewer than a dozen papers across his entire career. He told The Guardian in 2013 that he would not be productive enough for today's academic system, and he was probably right. Edinburgh University nearly fired him before his first Nobel nomination. Department authorities reportedly took the view that he might get a Nobel Prize, and if he did not, they could always get rid of him. His breakthrough came in 1964 after a failed camping weekend in the Scottish Highlands. The rain drove him home early, and on the way back, something clicked. A colleague recalled him saying, and this is a direct quote, "Oh shit, I know how to do that." He wrote the paper, he submitted it to physics letters at CERN, and they rejected it. The editor said it had no relevance to physics. Higgs added a paragraph predicting a new particle, submitted it elsewhere, and it was published. That particle, the one predicted in the extra paragraph of a rejected paper by a man who almost lost his job, is the particle that 50 years later told us the vacuum of space is not stable. And here is the part that should have made bigger headlines than it did. The safety arguments for the Large Hadron Collider, the machine that found this particle, depend on the same theoretical framework that just confessed its own incompleteness. We will come back to that. But keep it in mind, because the deeper we go into what CERN actually found, the less comfortable that fact becomes. The Higgs discovery was supposed to be the end of a search. It was supposed to close a chapter. The standard model was complete. Every particle it predicted had been found. Every force it described had been confirmed. The celebrations were real and deserved. But physics does not care about narratives. And the number 125.2 GeV did not cooperate with the story the institutions wanted to tell. Because the standard model was not just complete, it was suspiciously, disturbingly, almost offensively complete. There was nothing else. No extra particles, no supersymmetric partners, no dark matter candidates, no extended Higgs sectors, just the Higgs sitting exactly where the model said it would sit, at a mass that placed the entire universe on the edge of a cliff, with no new physics visible anywhere to explain why. Back in 2007, Adrian Cho had written a piece in Science magazine describing what he called the physicist's nightmare scenario, the Higgs and nothing else. At the time, virtually nobody took this seriously. The consensus was overwhelming. The LHC would find supersymmetry. It would find extra dimensions. It would drown in new particles. Beat Heinemann, a physicist at Decay who worked on the Atlas detector, captured the mood perfectly when she said before the LHC turned on that, one would drown in supersymmetric particles. They did not drown. They did not even get their feet wet. The nightmare scenario came true, and the scientific establishment that had bet its career trajectory, its funding model, its entire theoretical framework on finding something beyond the standard model was left holding a theory that works too well to abandon and too poorly to be the final answer. That tension, that impossible position, is what the rest of this story is about. Because CERN did not just find a crack in reality when it measured the Higgs mass. It found that the crack might be all there is. And then it found something worse. It found that every other crack it thought it had discovered was an illusion. To understand why the number 125 matters so much, you need to understand what the Higgs field actually is. Not the pop science version, not the analogy about particles wading through molasses, the real version, the version that keeps theoretical physicists awake. The Higgs field is not like other fields in physics. The electromagnetic field, for example, has a default state of 0. When nothing is happening, no charges nearby, the field sits at 0 and stays there. The Higgs field cannot do this. Its lowest available energy state is not at 0. It is at a specific non-zero value, approximately 246 GeV, and this value permeates every cubic centimeter of the observable universe. This is not a choice. If the Higgs field sat at 0, electrons would have no mass, protons would not form, atoms would not exist, and you would not be here to wonder about any of it. The entire material structure of reality depends on the Higgs field sitting at a value that is not 0. But sitting at a non-zero value means the field chose a position on an energy curve, and the shape of that curve matters enormously. If the curve has only one valley, one minimum, then the field is in a stable state and you can sleep at night. If the curve has two valleys, one shallow and one deep, then the field might be sitting in the shallow one. Stable enough to last a very long time, but not forever, not fundamentally. The shape of that curve depends on the Higgs mass. That is why 125.2 GeV is not just a measurement, it is a verdict. The relationship between the Higgs mass and vacuum stability was first investigated in 1979 by Nicola Cabibbo, Luciano Miani, Giorgio Parisi, and Riccardo Petronzio. They showed that the top quark's mass, through quantum loop corrections, could drag the energy curve downward at high field values. If the drag was strong enough, the curve would develop a second minimum deeper than the one we inhabit. For decades, This was a theoretical curiosity. Nobody knew the Higgs mass or the top quark mass well enough to say which side of the boundary the universe fell on. Then in 2012, they knew both numbers. The Higgs mass at 125.2 plus or minus 0.1 GeV, the top quark mass from combined ATLAS and CMS measurements at 172.52 plus or minus 0.33 GeV. When de Grassi and his collaborators plugged those numbers into the most precise calculation ever performed of the Higgs effective potential, the answer was clear. The quartic coupling lambda, the parameter that determines whether the energy curve bends upward or downward at extreme field values, crosses zero and goes negative at a scale of around 10 to the 10 GeV. The curve bends down. The second minimum exists, and it is deeper than ours. The idea that the universe might be sitting in a false vacuum was not new. The theoretical framework for vacuum decay had been worked out decades earlier by Sidney Coleman at Harvard. In 1977, Coleman published Fate of the False Vacuum, and in 1980, with Frank DeLucia, he extended the calculation to include gravity. The picture they painted was precise and terrifying. A bubble of true vacuum would nucleate at some random point in space through quantum tunneling. The bubble wall would expand outward at essentially the speed of light. Inside the bubble, the Higgs field would sit at its true minimum value, and every fundamental constant, every particle mass, every force would be different. Atoms as we know them would not form. Chemistry would not work. Life would not be possible. Coleman wrote a passage about this that haunts the physics literature to this day. He noted that one could always draw stoic comfort from the possibility that perhaps the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. And then he added, with the dry Harvard precision that made him legendary, this possibility has now been eliminated. Eliminated. Not made unlikely. Eliminated. The true vacuum at the bottom of the deeper valley would not support organized structures of any kind. Not atoms, not stars, not thoughts. And the transition would happen at light speed, which means zero warning. You would not see it coming. Not because you were not paying attention, but because the information that it was happening would arrive at exactly the same instant the bubble wall hit you. One moment you exist in a universe with atoms and light and time as you understand them. The next, you do not. And the word next is generous because the transition would take less time than light needs to cross a single proton. That was the theoretical framework. Disturbing but academic, as long as nobody knew whether the universe actually sat in a false vacuum. The Higgs discovery answered that question. And the answer was yes. Now, the institutions made a choice about what to say publicly. The press releases announced the Higgs boson. The Nobel Prizes were awarded. The media ran stories about the God particle and the triumph of modern physics. And the metastability of the vacuum, the single most consequential implication of the measured Higgs mass, was discussed in technical papers, at theoretical conferences, and essentially nowhere else. It was published, peer-reviewed, confirmed by multiple independent groups, and then quietly set aside. You could argue this was responsible. The expected decay time, calculated by Anders Andreasen, William Frost, and Matthew Schwartz at Harvard in 2018, is 10 to the 139 years. That is 10 to the 129 times the current age of the universe. On any human timescale, or any cosmological timescale, that number might as well be infinity. So why worry? That is a fair question, and we will answer it. But the answer requires understanding something that the press releases definitely did not mention. That decay time, that reassuring 10 to the 139, depends entirely on the standard model being the complete description of vacuum physics. Every quantum field accounted for, every coupling known, every possible tunneling pathway included. And the standard model is not complete. It is in fact broken in at least 7 fundamental, quantifiable, undeniable ways. Ways that have been known for decades. Ways that could change that lifetime calculation by factors that nobody, not a single physicist on Earth, can currently predict. The anomalies were supposed to help. In the years after the Higgs discovery, a series of experimental results emerged from CERN and other facilities that seemed to point beyond the standard model. Cracks, deviations from predictions, hints of new particles, new forces, new physics that might explain the vacuum metastability, and more importantly, protect against it. The physics community seized on these anomalies with something bordering on desperation, because if the standard model was the whole story, the situation was deeply uncomfortable. If something existed beyond it, there was hope that the full picture would be less bleak. One by one, the anomalies collapsed. The first ghost was called the flavor anomaly, and for nearly a decade, it looked like the most promising crack in the standard model that anyone had found since the discovery of neutrino oscillations. Here is what was supposed to happen. The standard model contains a principle called lepton universality. It is one of the theory's deep structural commitments. Electrons, muons, and tau particles are supposed to be treated identically by the electroweak force. Identical. Not similar. Not approximately the same. Identical up to trivial differences in mass. If you take a B-meson, a particle containing a bottom quark, and watch it decay into a kaon plus a pair of leptons, the standard model says the probability of getting a muon pair should be exactly the same as the probability of getting an electron pair. The ratio, called R of k, should be 1. In 2014, the LHCb experiment at CERN measured R of k and got 0.745. Not 1. Not even close to 1. The deviation was 2.6 sigma, which in physics means there was roughly a 1 in 100 chance it was a statistical fluke. Interesting, but not conclusive. In 2017, they measured a related quantity, R of k star, and found values of 0.66 and 0.69 in 2 different momentum bins. Each was more than 2 sigma low. The pattern was consistent. Muons were showing up less often than electrons. Something appeared to be treating leptons differently. By March of 2021, using the full Run 1 and Run 2 dataset, 9 inverse femtobarns of proton-proton collision data, LHCb reported an updated R of k of 0.846, 3.1 sigma. That number matters because 3 sigma is the informal threshold in particle physics for claiming evidence of a new phenomenon. They had crossed it. The result was published in Nature Physics. The paper generated hundreds of theoretical follow-ups proposing new particles, leptoquarks, Z-prime bosons, entire extended frameworks that could explain why the universe was not treating electrons and muons the same way. Think about what that meant for the vacuum metastability problem. If lepton universality was violated, the standard model was broken in a new and specific way. New particles would need to exist. New fields would contribute to the Higgs potential. The entire calculation of vacuum stability would need to be redone with those additional contributions. The metastability might get worse, or it might get better. But either way, the vacuum lifetime of 10 to the 139 years would be wrong, because the model it was based on would be incomplete in a way that actually affected the calculation. There was hope that whatever broke lepton universality would also stabilize the vacuum. Then, on December 20th, 2022, at a CERN seminar that most of the physics world watched in real time, LHCb presented a complete reanalysis of the same data. The new R of k was 0.949 plus or minus 0.047. Consistent with 1. Consistent with the standard model. Consistent with lepton universality. The 3.1 sigma anomaly was gone. It had been a systematic error all along. What happened was technical and, in hindsight, painfully mundane. Pions and kaons in the detector had been misidentified as electrons. These hadronic backgrounds contaminated the electron signal, making it look like fewer electrons were being produced than muons. When LHCb applied improved background rejection methods, the effect vanished. Chris Parkes, the LHCb spokesperson, attributed the change to an improved understanding of misidentified hadronic backgrounds. Gino Isidori at the University of Zurich, one of the theorists who had built his reputation on interpreting the anomalies, called the result a sudden cold shower. The community blog Particle Bytes noted with restrained frustration that some may be a tad frustrated that the checks which found these missing backgrounds were not done earlier, given how high-profile the measurements were. 8 years, hundreds of papers, entire careers redirected, and the crack was a miscount. But that was only the first ghost. The second one was louder, more dramatic, and when it died, it took an entire decade of work with it. On April 7, 2022, the CDF collaboration at Fermilab published what appeared to be the single most devastating blow to the Standard Model in a generation. Their measurement of the W boson mass, one of the most fundamental parameters in all of particle physics, came in at 80,433.5 plus or minus 9.4 MeV. The Standard Model prediction was 80,357 plus or minus 6 MeV. The difference was 76.5 MeV. The statistical significance was 7 sigma. In a field where 5 sigma counts as a discovery, 7 sigma was seismic. The analysis lead was Ashutosh Kotwal at Duke University, and he had spent a decade on it. The measurement used 4.2 million W boson candidates from Tevatron collision data, and it had been blinded, meaning the physicists doing the analysis could not see their final number until every systematic check was complete. They unblinded on November 19, 2020. What they saw was the largest deviation from the Standard Model ever measured in a precision electroweak observable. If confirmed, it would demand new particles or forces, supersymmetric partners, extended Higgs sectors, new gauge bosons, something. The physics community exploded. A team led by Athran and collaborators showed that the CDF anomaly and the Muon G-2 anomaly, which we will get to in a moment, pulled the theoretical predictions in opposite directions, meaning if both were real, new physics was inescapable regardless of how you calculated the theory uncertainties. For a brief window, it looked like the Standard Model was crumbling from multiple directions at once. It was not. Every other measurement of the W boson mass, from every other experiment, agreed with the Standard Model. Atlas had measured 80,370 plus or minus 19 in 2017. The LEP experiments at CERN had found 80,376 plus or minus 33. The D0 experiment at the same Tevatron that CDF used found 80,375 plus or minus 23. And LHCb measured 80,354, all of them clustered within 20 MeV of the Standard Model prediction. CDF stood alone, 76 MeV away, like a single witness contradicting every other person in the room. Then the decisive responses came. In March of 2024, Atlas published an updated measurement using improved statistical methods. 80,366.5 plus or minus 15.9 MeV, consistent with the Standard Model. And in September of 2024, CMS released its first ever W mass measurement, one that had taken years to complete, using over 100 million reconstructed W bosons from 13 TeV collision data. The result was 80,360.2 plus or minus 9.9 MeV, matching CDF's precision, consistent with the Standard Model. A direct contradiction. The LHCb W mass working group ran a statistical combination of all measurements and found that including CDF's result yields only 0.5% probability of compatibility with everything else. Excluding CDF restores 91% compatibility. The conclusion was unspoken but clear. CDF was wrong. David Toback, the CDF spokesperson, said in 2024 that the collaboration does not have an explanation for the incompatibility. They have not retracted. But the physics community has moved on. The W boson mass anomaly was a ghost. 2 ghosts down, the escape routes were closing. But there was one more, and this one had been running longer than either of the others. The Muon G-2 anomaly was the oldest, and for many physicists, the most beautiful precision test of the Standard Model. The anomalous magnetic moment of the muon, a quantity designated A sub mu, is sensitive to virtual contributions from every particle that exists, including particles we have not discovered yet. If you measure it precisely enough and predict it precisely enough, the difference between measurement and prediction is a window into hidden physics. For 2 decades, that window appeared to be open. In 2006, the Brookhaven E821 experiment measured A sub mu to extraordinary precision and found a discrepancy with the Standard Model prediction. The tension grew with Fermilab's Run 1 result, announced on April 7, 2021, exactly 1 year before the CDF bombshell. The combined Brookhaven and Fermilab value showed a 4.2 sigma discrepancy from the theory prediction published in the Theory Initiative's 2020 white paper, 4.2 sigma, just below the discovery threshold, but tantalizing. The white paper prediction was based on what is called the dispersive method, which uses experimental data from electron-positron collisions to estimate the dominant theoretical uncertainty, the hadronic vacuum polarization contribution. Then the theory moved, and it moved in the wrong direction. The BMW Lattice QCD collaboration, a group that calculates hadronic contributions from first principles using supercomputers, published a result in Nature in 2021 that was substantially higher than the dispersive prediction. If BMW was right, the Standard Model prediction was higher, and the gap with experiment was smaller, much smaller. Multiple independent lattice groups, CLS mains, ETMC, RBC UKQCD, Fermilab HPQCD MILC, and ChiQCD, subsequently converged on similar values. The lattice calculations agreed with each other and disagreed with the dispersive method. The situation became even more tangled when the CMD 3 experiment in Novosibirsk measured the critical electron-positron to pion pair cross-section and found values systematically higher than all previous measurements. In roughly 5 sigma tension with the KLOE experiment in Italy, if CMD 3 was right, the dispersive method would also agree with experiment. If KLOE was right, the dispersive method was correct and something else was wrong. The 2025 Theory Initiative white paper declared it impossible to combine the data-driven results in a meaningful way. On June 3, 2025, Fermilab released its final result from all 6 data-taking runs spanning 2018 through 2023. 100 billion muon decay events, the most precise measurement of this quantity ever performed, at 127 parts per billion. Exceeding the experiment's original design goal. The number agreed perfectly with all previous measurements. The experiment was not the problem. The 2025 white paper made a historic shift. It adopted lattice QCD as the basis for its recommended Standard Model prediction. The new prediction yields a discrepancy with experiment of only 0.6 sigma. The anomaly that had sustained 2 decades of hope for new physics had evaporated. Not because the experiment was wrong, but because the theory recalculated itself into agreement. The theoretical uncertainty at 530 parts per billion is now 4 times larger than the experimental uncertainty. The theorists need to catch up. And until they do, the window into new physics that the Muon anomaly once provided is closed. 3 anomalies, 3 collapses. The flavor anomaly was a systematic error in background identification. The W boson mass anomaly was an isolated measurement contradicted by every other experiment. The Muon G-2 anomaly dissolved when the theoretical prediction was recalculated from first principles. And here is what the media reported after each collapse. Standard model holds. Physics confirmed. Everything works. The headlines treated each collapse as a victory, as proof that the standard model was right all along. The implication was that the crisis in physics was over, that the worries had been overblown, that the theory was fine. This is the misconception you need to let go of right now. The collapse of the anomalies did not make things better. It made things worse, because the anomalies were escape routes. Each one offered a direction, a hint, a thread that experimentalists could follow to whatever physics lies beyond the standard model. Whatever physics might explain why the vacuum is metastable, or what dark matter is, or why the cosmological constant is off by 120 orders of magnitude. Without those threads, the standard model's permanent, structural, unfixable failures are all that remain. And those failures are far more disturbing than any anomaly that came and went. The standard model of particle physics is the most precisely tested theory ever constructed by human beings. Its predictions have been verified to 11 decimal places. It describes 3 of the 4 fundamental forces. It accounts for every particle ever detected in a collider. It predicted the existence of the Higgs boson half a century before it was found. And it knows it is wrong. This is not an interpretation. This is not a matter of debate among physicists. The standard model contains at least 7 specific, quantifiable, undeniable failures, each one representing a gap between what the theory predicts and what the universe actually does. These are not anomalies that might vanish with better data. They are structural confessions built into the theory's foundations. They have been there since the 1970s. And not a single one of them has gotten smaller. The first confession is the cosmological constant problem, and it is routinely called the worst prediction in the history of science. Not the worst prediction in the history of physics. The worst prediction in the history of science. Quantum field theory, the mathematical framework underlying the standard model, predicts that empty space should have an energy density. This is not speculative. Vacuum energy is a direct consequence of the uncertainty principle. Virtual particles flicker in and out of existence everywhere, all the time, and their combined contribution gives the vacuum a non-zero energy. When you calculate that energy using a Planck scale cutoff, the number you get is approximately 10 to the 71 GeV to the 4th power. The observed value, measured from the accelerating expansion of the universe, is roughly 2.9 times 10 to the minus 3 eV to the 4th. The discrepancy between prediction and observation is a factor of 10 to the 120. Let that sit for a moment. Not 10 to the 10, not 10 to the 50, 10 to the 120. If you asked a physicist to name the single biggest disagreement between theory and experiment in any field, this is it. There is no close second, and nobody has a widely accepted solution. Not string theory, not loop quantum gravity, not any of the hundreds of proposed modifications to general relativity or quantum field theory that have been tried since this problem was first identified in the late 1960s. The vacuum energy of the universe disagrees with the standard model's prediction by 120 orders of magnitude, and the best theoretical physics on the planet cannot explain why. The second confession is the hierarchy problem. The Higgs boson has a mass of 125 GeV. Quantum corrections from virtual particles should push that mass toward the Planck scale, which is 10 to the 18th GeV. The difference between the Higgs mass and the Planck scale is 16 orders of magnitude. For the Higgs to have a mass of 125 GeV, the bare mass parameter and the quantum corrections must cancel each other to a precision of 1 part in 10 to the 32. Unlike fermion masses, which are protected by chiral symmetry, and gauge boson masses, which are protected by gauge symmetry, scalar particles like the Higgs have no symmetry shielding them from ultraviolet corrections. The Higgs mass is naked. Every heavy particle in the universe contributes quantum corrections to it, and those corrections are enormous. For the final number to be 125 GeV, an almost inconceivable cancellation must occur. As Matt Strassler has written, the Higgs has a snowball's chance in hell of having a mass in that ballpark. The leading solution for decades was supersymmetry. For every particle in the standard model, supersymmetry proposes a partner particle whose contribution to the Higgs mass would exactly cancel the original particle's contribution. The cancellation would be natural, not fine-tuned. But supersymmetry requires those partner particles to exist, and the LHC has not found them. Gluino exclusion limits have reached 2.3 to 2.4 TeV. Every year that passes without a supersymmetric partner being discovered makes the fine-tuning problem worse, because heavier partners mean less precise cancellation. The solution to the hierarchy problem has itself become a hierarchy problem. The third confession is the strong CP problem. The strong nuclear force, described by quantum chromodynamics, contains a parameter called theta bar that could in principle take any value from 0 to 2 pi. If theta bar is not 0, the strong force would violate a symmetry called CP, the combined symmetry of charge conjugation and parity inversion. That violation would manifest as a measurable electric dipole moment of the neutron. The neutron electric dipole moment has been measured to extraordinary precision by the NIDM experiment at PSI in Switzerland. The result is that it is less than 1.8 times 10 to the minus 26 centimeters at 90% confidence. This constrains theta bar to be less than approximately 2 times 10 to the minus 10. A number that should be of order 1 turns out to be smaller than 1 in 10 billion. The standard model has no explanation for why. It is a fine-tuning of 1 part in 10 to the 10, and unlike the hierarchy problem, there is no symmetry argument that even comes close to resolving it. The most popular proposed solution, the Peckier-Quinn mechanism, predicts a new particle called the axion. The axion has not been found. The fourth confession involves the matter that makes up everything you can see and touch. After the Big Bang, the universe should have produced equal amounts of matter and antimatter. The standard model's mechanism for breaking that symmetry, CP violation through the CKM matrix, is real and measured, but it is spectacularly insufficient. The baryon to photon ratio, the number that quantifies how much more matter exists than antimatter, is measured from the cosmic microwave background and Big Bang nucleosynthesis at approximately 6.1 times 10 to the minus 10. The standard model predicts a value of roughly 10 to the minus 18, 8 orders of magnitude too small. Whatever created the matter you are made of, the standard model cannot account for it. Not even close. The fifth confession is dark matter, and it is probably the most famous failure on this list, though not the most dramatic. Observations of galaxy rotation curves, gravitational lensing, the cosmic microwave background, and large-scale structure formation all converge on the same answer. Ordinary matter, the stuff the standard model describes, accounts for about 5% of the energy content of the universe. Dark matter accounts for 26.5%, as measured by the Planck satellite with extraordinary precision. Omega sub ch squared equals 0.120 plus or minus 0.001. The standard model does not contain a particle that could be dark matter, not one. Direct detection experiments, LZ, XENONT, PandaX, have pushed the sensitivity for dark matter interactions below 10 to the minus 47 square centimeters, and they have found nothing. Whatever dark matter is, it is not in the standard model, and 25 years of searching have not found it. The sixth confession is that neutrinos have mass. The standard model, as originally constructed, predicts that neutrinos are massless. They are not. Neutrino oscillation experiments have definitively proven that neutrinos change flavor as they travel, which is only possible if they have non-zero mass. The mass squared differences are precisely measured. Delta m squared 21 equals 7.42 times 10 to the minus 5 eV squared. The absolute value of delta m squared 32 equals 2.51 times 10 to the minus 3 eV squared. Katrin, the world's most sensitive direct neutrino mass experiment, reported in April 2025 an upper bound of 0.45 e. At 90% confidence, the masses are tiny but real. Neutrino mass is the only laboratory-confirmed departure from the standard model, and the theory has no mechanism to generate it. You have to add new fields, new symmetries, new physics to give neutrinos mass. And nobody knows what that new physics is. The seventh confession is the Hubble tension, and unlike the others, this one has gotten worse with time. Two independent methods of measuring the expansion rate of the universe give answers that disagree at roughly 5 sigma. The Planck satellite, measuring the cosmic microwave background from the early universe, gives a Hubble constant of 67.4 plus or minus 0.5 kilometers per second per megaparsec. The SH0ES project, measuring Cepheid variable stars and type Ia supernovae in the local universe, gives 73.17 plus or minus 0.86. The difference is about 8%. For years, the assumption was that one measurement had a systematic error. The James Webb Space Telescope was supposed to settle it by providing higher resolution observations of the Cepheid stars that anchor the distance ladder. It confirmed that the Hubble Space Telescope measurements were accurate. The Cepheids are not the problem. 5 sigma is the threshold for a discovery in particle physics. By that standard, the Hubble tension is a discovery that the early universe and the late universe disagree about how fast reality is expanding. 7 confessions. 7 places where the standard model either gets the answer catastrophically wrong, gives no answer at all, or requires fine-tuning so extreme it borders on absurdity. And every single one of them was known before the Higgs boson was discovered. Every single one of them is still there, unchanged, unfixed, and in several cases, growing worse with better data. This is the part of the story that does not make headlines. When the flavor anomaly collapsed, the media said the standard model won. When the W boson mass anomaly was contradicted, the standard model won again. When the Muon G-2 gap disappeared, the standard model won a third time. And technically, that is correct. The model survived. Its predictions were right, or at least not provably wrong, in each specific case. But surviving is not the same as being correct. A theory that correctly predicts the behavior of 5% of the universe and has nothing to say about the other 95% has not won anything. It has survived its own limitations by the narrowest possible margin, and the escape routes that might have pointed towards something better are now closed. This brings us to the man who helped build the model in the first place, and whose story tells you everything about how institutions treat the things they do not want to face. Abdus Salam was born on January 29, 1926, in Jang, in the Punjab region of what was then British India. He was a prodigy. He topped the Punjab University matriculation exam at age 14 with the highest score ever recorded. He earned a degree from Cambridge, a PhD, and went on to become one of the 3 architects of the electroweak theory. the unification of the electromagnetic and weak nuclear forces that forms the backbone of the Standard Model. In 1979, he shared the Nobel Prize with Sheldon Glashow and Steven Weinberg. He was the first Muslim Nobel laureate in any science. During his acceptance speech, he quoted the Quran. Salam was a devout member of the Ahmadiyya Muslim community. In 1974, Pakistan's government passed a constitutional amendment declaring Ahmadis non-Muslim. Salam left Pakistan in protest. He never lived there again. He said, "The day you declared me a non-Muslim is the day you made me a second-class citizen." He refused citizenship offers from India, Italy, and the United Kingdom, remaining a Pakistani citizen until his death on November 21, 1996, from progressive supranuclear palsy. He was 70 years old. No government official attended his funeral. His tombstone originally read, "First Muslim Nobel Laureate." A local magistrate, citing Pakistan's 1984 ordinance, X2X, ordered the word Muslim erased. Someone physically scraped it off the stone. The epitaph now reads, "In 1979, became the first blank Nobel laureate for his work in physics." The blank where Muslim was whitewashed out is visible. You can see where the letters used to be. Think about that. One of the three people most responsible for the theory that describes the forces holding your atoms together, a theory that has been verified to 11 decimal places, had his identity physically erased from his own grave by the country he refused to abandon. The Standard Model knows it is incomplete, and the man who helped build it was erased. There is a parallel here that is not subtle. The Standard Model's failures are known. They are quantified, they are published in every textbook, and they are quietly set aside in public communication, papered over with headlines about precision tests confirmed and anomalies defeated, just as Salam's contribution to Pakistan's scientific heritage was literally scraped from stone. The erasure is different in kind, but identical in function. Inconvenient truths made invisible. And every one of those 7 confessions affects the vacuum metastability calculation. Every undiscovered particle that the Standard Model is missing, every field it does not describe, every coupling it does not include, changes the shape of the Higgs potential at high energies. The quartic coupling lambda, the parameter that determines whether the vacuum is stable or metastable, receives contributions from every quantum field in existence. If there are fields we do not know about, the calculation is wrong. Not wrong by a little, wrong in a way that we cannot quantify, because we do not know what we do not know. The safety arguments for high-energy particle colliders depend on the Standard Model's description of how vacuum decay works. They depend on the tunneling rate calculation. They depend on the shape of the Higgs potential. And we have just spent the last several thousand words establishing that the Standard Model cannot account for 95% of the energy content of the universe, cannot explain why the cosmological constant is not 10 to the 120 times larger than observed, and cannot generate the masses of the particles it knows are massive. That should make you uncomfortable. But the 7 confessions are not the crack in reality that the title of this story promised. They are the context, the background radiation of a theory in crisis. The crack is something more specific, more visceral, and more difficult to dismiss. Let us go back to the Higgs potential, the energy curve, the shape that determines whether the universe is stable or perched on a shelf. When physicists say the quartic coupling lambda goes negative, here is what they mean in practical terms. Imagine a landscape. At the origin, where the Higgs field value is 0, there is a hill. The field rolled off that hill in the first fractions of a second after the Big Bang and settled into a valley at 246 GeV. That valley is your universe, your atoms, your chemistry, your consciousness. Everything you know and are exists because the Higgs field sits at the bottom of that valley. Now zoom out. Follow the energy curve to higher and higher field values. For a while, it climbs. The walls of the valley rise on either side. This is the barrier, the thing protecting you. But at a field value of around 10 to the 10 GeV, the curve stops climbing and starts to bend. It flattens, and then, slowly, it begins to drop. The walls of the valley are not infinite. They peak, and beyond the peak, the landscape falls away into a second deeper depression. A second valley. The true minimum. The reason it drops is the top quark. The top quark is the heaviest elementary particle in the Standard Model, with a mass of 172.52 GeV. Its Yukawa coupling to the Higgs field is enormous. Close to 1, and through quantum loop corrections, it drags the quartic coupling downward. The other particles in the Standard Model, the gauge bosons, push lambda upward. It is a tug of war, and for the specific values of the Higgs mass and the top quark mass that nature chose, the top quark wins. Lambda crosses zero and goes negative. The barrier peaks and the landscape falls. Now, the critical question. How high is the barrier? Because the barrier height determines how long the false vacuum survives. A higher barrier means a lower tunneling probability, which means a longer lifetime. A lower barrier means the opposite. In 2018, Anders Andreasen, William Frost, and Matthew Schwartz at Harvard performed the definitive calculation. Their paper, published in Physical Review D, computed the tunneling rate at full next to leading order in the Standard Model, including gravitational corrections. The result was a vacuum lifetime of approximately 10 to the 139 years. That number deserves context. The current age of the universe is about 13.8 billion years, or roughly 10 to the 10 years. The vacuum lifetime is 10 to the 139 years. That is not 10 to the 39 or 10 to the 69. It is 10 followed by 139 zeros. The ratio of the vacuum lifetime to the age of the universe is 10 to the 129. On any timescale that has any physical meaning, the vacuum is safe, except that number was revised. A 2024 correction by the same group identified a previously overlooked contribution to the gauge field sector that increased the tunneling rate by a factor of roughly 10 to the 6th. A factor of 1,000,000 sounds dramatic, but when your starting point is 10 to the 139, multiplying the rate by 1,000,000 brings the lifetime down to 10 to the 133 years. Still incomprehensibly safe by any standard. So why am I telling you this? If the vacuum is going to last 10 to the 133 years, roughly 10 to the 123 times the age of the universe, why should you care? Why should anyone? Because that number is a castle built on sand. The Andreasen calculation assumes the Standard Model is the complete description of particle physics up to the Planck scale. It includes every field in the Standard Model, every coupling, every quantum correction that those fields generate. And then it stops. It assumes nothing else exists. No dark matter particles, no axions, no right-handed neutrinos, no supersymmetric partners, no extra dimensions, no hidden sectors. Nothing. We just catalogued 7 reasons to believe this assumption is false. The Standard Model cannot explain dark matter, which constitutes 26.5% of the universe. It cannot explain dark energy, which constitutes another 68.5%. It cannot generate neutrino masses without new fields. It cannot produce enough CP violation for baryogenesis without new sources. It cannot explain why the strong CP parameter is fine-tuned to 1 in 10 billion without new symmetries. The Higgs mass itself requires fine-tuning to 1 part in 10 to the 32 without new particles. Every one of those missing pieces, every undiscovered field, every unknown coupling contributes to the Higgs effective potential. And contributions to the Higgs potential change the shape of the energy landscape. They change the height of the barrier, they change the depth of the true minimum, They change the tunneling rate. In some scenarios, new fields stabilize the vacuum completely. In others, they destabilize it dramatically. And in most scenarios, we simply do not know what they do, because we do not know what they are. The lifetime of 10 to the 133 years is the answer you get if you assume we know everything. We know we do not know everything. The standard model is missing at least 95% of the universe's content, and the vacuum lifetime calculation depends on the complete particle content of nature in a way that is not negotiable. You cannot separate the metastability question from the dark matter question, or the hierarchy problem, or the neutrino mass problem. They are all connected through the Higgs potential. Get any of them wrong, and the lifetime changes in ways that could be trivial or could be catastrophic. This is what makes the Higgs field feel less like a passive background and more like something else entirely. It permeates everything. It determined the conditions for atoms to exist, and it chose a value settled into a configuration that the math says is not the deepest available option. You can call it a quantum fluctuation that froze during symmetry breaking. You can call it the vacuum expectation value dictated by the Mexican hat potential. But strip away the jargon, and what you have is a field that occupies every point in the universe, that holds a position the equations say is temporary, and that has been holding it for 13.8 billion years. The Higgs field does not just exist in the universe. In a very real sense, the Higgs field is the universe, and it is patient. Sidney Coleman understood this better than almost anyone. He was, by all accounts, the most gifted physicist of his generation who did not win a Nobel Prize. His Harvard lectures were legendary, not just for their content, but for their clarity and their wit. Graduate students who studied under him in the 1970s and 80s describe a mind that operated differently from other minds, one that saw through mathematical formalism to the physical reality underneath in a way that was almost uncanny. When a colleague said something pretentious, Coleman would cut through it with a line that was simultaneously a joke and a devastating criticism. "Modesty forbids me, but honesty compels me," he would say. And you understood that both parts were true. He spent the better part of a decade thinking about vacuum decay. His 1977 paper, Fate of the False Vacuum, established the semi-classical method for calculating the tunneling rate using what he called the bounce solution, an instanton that interpolates between the false and true vacuum configurations. The mathematics is elegant in a way that only field theory can be. The bounce is a saddle point of the Euclidean action, a path through field configuration space that represents the quantum mechanical probability of the field finding its way through the barrier. Coleman showed that this probability is exponentially suppressed by the action of the bounce, which means the tunneling rate is exponentially small, safe in other words, but not zero, and exponentially small in a way that depends on the exact shape of the potential, which depends on the exact particle content of the theory. When he extended the calculation to include gravity with De Lucia in 1980, the results were even more striking. Gravity changes the nature of the true vacuum interior. Without gravity, the inside of the bubble is simply a different vacuum, a region of space where the fundamental constants are different. With gravity, depending on the sign and magnitude of the cosmological constant in the true vacuum, the interior can be a collapsing region, a universe that immediately begins contracting toward a singularity. The structures capable of knowing joy that Coleman mentioned would not merely be reconfigured, they would be crushed by the geometry of space-time itself. Coleman wrote about this with the dry precision that made him legendary among physicists, and the passage he produced has stayed in the minds of everyone who has read it for 45 years. He died in 2007 after years of declining health. His former students describe him as irreplaceable, a mind that combined mathematical rigor with a poet's instinct for what the equations actually meant, not just what they calculated. He did not live to see the Higgs discovery, He did not live to learn that his framework, his bounce solution, his tunneling calculation, applied not to a hypothetical situation, but to the actual universe. The bubble does not form at a single point and grow slowly. It forms as a finite sphere whose radius is determined by the competition between the energy gained by being in the true vacuum and the energy cost of the bubble wall. Once the bubble reaches its critical radius, the outward pressure from the energy difference overwhelms the inward tension of the wall, and the bubble begins to expand. It accelerates. Very quickly, it reaches a velocity indistinguishable from the speed of light. And because nothing, no signal, no warning, no information of any kind, can travel faster than light, the bubble is invisible to everyone outside it until the instant it arrives. Think about what that means for you specifically. If a bubble of true vacuum nucleated anywhere within our past light cone and began expanding, you would have no way of knowing. There is no detector you could build, no telescope you could point, no early warning system that physics permits that could tell you the bubble was coming. The first evidence of its existence would be its arrival. And its arrival would not be an event you experience. It would be the end of the concept of experience. The fundamental constants inside the bubble would not support chemical bonds. They would not support the electrochemical processes that constitute thought. You would not die in any meaningful sense, because dying requires a before and an after. There would be no after, just a different physics propagating through the space where you used to exist, at the speed of light, forever. Coleman knew this. He articulated it with a precision that was almost gentle, and the passage he wrote about structures capable of knowing joy being eliminated has stayed in the minds of physicists for 45 years. He died in 2007, after years of declining health. His former students describe him as irreplaceable, a mind that combined mathematical rigor with a poet's instinct for what the equations meant, not just what they calculated. And here is the thing Coleman could not have known. In 1980, the Higgs boson had not been discovered. The top quark had not been discovered. The mass values that determine whether the universe is stable, metastable, or unstable were unknown. Coleman worked out the general framework. He showed what would happen if the vacuum was false. He could not say whether it was. Now we know the Higgs mass is 125.2 plus or minus 0.11 GeV. The top quark mass is 172.52 plus or minus 0.33 GeV. Those two numbers, plotted on the phase diagram of vacuum stability, place the universe firmly in the metastable region, not near the boundary, not on the edge where a small change might tip it to stable. Firmly in the metastable zone, at 98% confidence. For absolute stability, you would need a Higgs mass of approximately 127.85 GeV. That is 24 standard deviations above the measured value. For practical purposes, it is ruled out. Alternatively, you would need a top quark mass of approximately 171.1 GeV, which is only 1.9 sigma below the current central value. A tantalizing margin, one that might narrow or widen as measurements improve. Future electron-positron colliders like the FCCE could measure the top mass to below 100 MeV precision, definitively nailing down whether stability is even mathematically possible. But with current data, metastability is not a possibility. It is the result. The shelf is real. The deeper valley exists. And the only thing between you and it is a barrier whose height depends on physics we have already established we do not fully understand. The standard model says the barrier is enormous, and the tunneling time is 10 to the 133 years. But the standard model also says the cosmological constant should be 10 to the 120 times larger than it is. The standard model says neutrinos should be massless. The standard model cannot find 95% of the universe, When the same model that is wrong about 120 orders of magnitude of vacuum energy tells you the vacuum lifetime is safe, you are entitled to ask how much weight that reassurance carries. And the honest answer, the answer that physicists acknowledge in private conversations and in the technical literature, but not in press releases, is that they do not know. They cannot know. Because the vacuum lifetime depends on the complete particle content of nature, and the complete particle content of nature is unknown. This is not speculation. This is what the published, peer-reviewed physics says. The vacuum is metastable. The lifetime depends on unknown physics. The uncertainty is not quantifiable. And the machine at CERN that is currently producing the highest energy particle collisions in human history sits on a planet inside that metastable vacuum, running at 13.6 trillion electron volts, slamming protons together 50 million billion times and counting. Which brings us to the machine itself. The Large Hadron Collider is a 27-kilometer ring buried beneath the French-Swiss border, roughly 100 meters underground, and it is the most complex machine ever constructed by human beings. That is not hyperbole. The magnets that bend the proton beams operate at 1.9 Kelvin, colder than outer space. The beams themselves contain 3,000 bunches of approximately 100 billion protons each, circulating at 99.999% of the speed of light, crossing each other at 4 points around the ring roughly 40 million times per second. Each crossing produces an average of about 40 simultaneous proton-proton collisions. Over the lifetime of the machine, it has produced something on the order of 50 million billion collisions. And in all of those collisions, across all of those crossings, at energies that nothing on Earth has matched since the machine was switched on, the standard model has not broken. Not once. Run 3 began in 2022 at a record center of mass energy of 13.6 TeV. Through early 2206, the machine has delivered approximately 280 inverse femtobars of collision data to each of the 2 general-purpose detectors, ATLAS and CMS. The lifetime total per experiment is now roughly 500 inverse femtobars, half an attobarn. And the results have been, from the perspective of anyone hoping for a crack in the theory, brutally confirmatory. The most significant discovery from Run 3 is arguably toponium, evidence for a quasi-bound state of a top quark and an anti-top quark. Atlas observed it at 7.7 sigma significance, with a cross-section of 9.0 plus or minus 1.3 picobarns. If confirmed, it is the heaviest quarkonium state ever found. CMS saw a consistent excess, but it is a standard model prediction. It is not new physics. It is old physics being confirmed at higher precision. LHCb achieved the first observation of CP violation in baryonic decays, a milestone that had been sought for decades. The decay of a lambda B baryon into a proton, a kaon, and 2 pions showed a CP asymmetry at 5.2 sigma significance, published in Nature in 2025. This is significant because CP violation had previously been observed only in mesons, and extending it to baryons was a major experimental achievement. But the size of the effect is consistent with the standard model. It is nowhere near large enough to explain the matter-antimatter asymmetry. The standard model predicts a baryon-to-photon ratio of 10 to the minus 18. The observed ratio is 6.1 times 10 to the minus 10, 8 orders of magnitude. The new CP violation in baryons does not close that gap. It does not even scratch it. All Higgs boson properties measured during Run 3 remain stubbornly standard model consistent. The coupling modifiers for W, Z, top-bottom tau, and photon channels all cluster around 1.0. Atlas reported 3.4 sigma evidence for the Higgs decaying to a pair of muons. which strengthens the case that the Higgs couples to second-generation fermions as the Standard Model predicts. No CP violation has been found in the Higgs sector. The combined Atlas CMS limit on di-Higgs production sits at 2.5 times the Standard Model prediction. Every measurement says the same thing. The Higgs behaves exactly as the Standard Model says it should, exactly as the theory that tells you the vacuum is metastable says it should. There is a particular cruelty to this. The same measurements that confirm the Standard Model's predictions are the measurements that confirm the Standard Model's implications. You cannot celebrate the precision of the Higgs coupling measurements and then ignore the vacuum stability analysis that those measurements feed into. The couplings that are confirmed at 1.0 are the couplings that, when run up to high energies through the renormalization group equations, produce a quartic coupling that crosses zero and goes negative. Every successful Higgs measurement is simultaneously a confirmation that the vacuum is metastable. The triumph and the confession are the same data point. And the particles that were supposed to exist, the ones that naturalness predicted, the ones that were supposed to solve the hierarchy problem and stabilize the vacuum and point the way toward whatever lies beyond the Standard Model, they are not there. Supersymmetric gluinos are excluded, up to 2.3 to 2.4 TeV. Stop squarks up to approximately 1 TeV. The searches have not found a single superpartner. They have not found a single extra dimension. They have not found a single dark matter candidate produced in a collision. They have found exactly what Adrian Cho warned about in 2007, the Higgs and nothing else. Nima Arkani-Hamed, one of the most influential theoretical physicists alive, described the fine-tuning problem with an image that has become famous in the field. He said that discovering a 125 GeV Higgs with no new particles is like walking into a room and seeing a pencil standing on its tip in the middle of a table. You know something is holding it up. Gravity alone does not explain the configuration. But when you look around the room for what that something might be, the room is empty. Arkani-Hamed himself was, by his own admission, a firm believer in naturalness for most of his career. He expected the LHC to find supersymmetry. When it did not, he did not deny the data. He adapted. By 2013, he had largely abandoned strict naturalness. In 2016, he proposed a framework called N-naturalness, published in Physical Review Letters, that attempted to explain the hierarchy without requiring new particles at the electroweak scale. He has spoken about the current moment in physics with a seriousness that stands out even among serious people. The stakes are higher than the past, he said. We are not asking about this or that particle, but something much more deeply structural about physical reality. Gianfrancesco Giudice, the head of CERN's own theory division, went further. In a 2017 paper that has become one of the most cited theoretical physics papers of the decade, he declared that physics had entered what he called the dawn of the post-naturalness era. Read that again. The head of the theory division at the institution that built the LHC published a paper arguing that the foundational principle which justified building the LHC might be wrong. He compared the moment to a Kuhnian paradigm shift, the kind of crisis that forces an entire field to rebuild its conceptual foundations. This was not a critic on the outside throwing stones. This was the architect looking at the building and saying the foundation may need to be replaced. Nathan Seiberg at the Institute for Advanced Study in Princeton, one of the most respected mathematical physicists in the world, said it plainly. 10 or 20 years ago, he was a firm believer in naturalness. Now he is not so sure. That is a seismic admission from a man whose career was built on the mathematical structures that naturalness implied. Sabine Hossenfelder became the most visible public critic of the naturalness paradigm. Her 2018 book, Lost in Math, argued that aesthetic criteria, beauty, symmetry, naturalness, mathematical elegance, had replaced empirical evidence as the guiding principles of theoretical physics, and that this had led the field astray for decades. Her central argument was devastating in its simplicity. Theoretical physicists used to explain what was observed, she wrote. Now they try to explain why they cannot explain what was not observed. Her YouTube channel, with over 1.7 million subscribers, brought the crisis to an audience that had never heard of the hierarchy problem or the naturalness principle, and her positions drew sharp responses from the establishment. Sheldon Glashow, one of the 3 Nobel laureates who built the electroweak theory, reviewed her book and pushed back. "I do like the standard model," he wrote. "I like it very much. I remember times when we knew practically nothing about elementary particles." That exchange captures the fault line perfectly. Glashow, who helped create the theory, defends it. Hossenfelder, who watches it fail to produce new predictions, attacks the methods used to extend it. And meanwhile, the machine keeps running, the collisions keep happening, and the data keeps saying the same thing. The standard model is correct. The standard model is incomplete. And those two statements are simultaneously true. The institutional response to this crisis has followed a predictable pattern. When the LHC found the Higgs and nothing else, the physics community did not sit down and ask what they had gotten wrong about naturalness. They proposed building a bigger machine. The Future Circular Collider, or FCC, would be a 100-kilometer ring, nearly 4 times the circumference of the LHC, capable of colliding protons at energies up to 100 TeV. It would cost an estimated 20 billion euros or more and take decades to build. The stated physics case is to measure Higgs boson properties with exquisite precision and search for new particles at energies far beyond the LHC's reach. The unstated reality is that the FCC is a bet that whatever lies beyond the standard model exists at energies the LHC cannot reach, but the FCC can. And it is a bet being placed at a time when the principle that predicted new physics at the LHC's energy scale, naturalness, has just been discredited by the LHC's own data. The question that nobody in the proposal documents wants to confront is straightforward. If naturalness was wrong about the TeV scale, why should anyone believe the next energy scale up will be different? The FCC proposal also raises a deeper question about the relationship between what physicists hope to find and what the vacuum metastability calculation actually needs. The metastability depends on the running of the quartic coupling at energies between the electroweak scale and the Planck scale, a span of roughly 16 orders of magnitude. New particles at any point in that range can alter the running and change the vacuum lifetime. But the FCC would probe energies up to approximately 100 TeV. That is barely above where the LHC currently operates, and it is roughly 5 orders of magnitude below the scale where the quartic coupling crosses 0. In other words, even the 100 TeV machine would be probing less than 1/3 of 1% of the energy desert between the electroweak scale and the instability scale. Whatever is out there, statistically speaking, is almost certainly beyond the reach of any collider that could be built in the 21st century. The only way the FCC finds something relevant to vacuum stability is if new physics happens to appear very close to the current energy frontier. And naturalness, the principle that predicted exactly that, just failed. The parallel to Abdus Salam's story is hard to miss. Salam dedicated his career to a theory that describes the electroweak force, a theory that has been verified to extraordinary precision, and his own country responded by erasing his identity from a gravestone. The standard model that Salam helped build is now in a similar position. Its creators built something that works spectacularly well, and the institutions that should be celebrating its achievements and honestly confronting its failures are instead doing a version of the same thing Pakistan did to Salam's tombstone. Not erasing the failures, exactly, but rendering them invisible in the public narrative, leaving a blank where the uncomfortable truth should be. You can visit Salam's grave in Bahishti Maqbara Cemetery in Rabwa, Pakistan, and see the blank space where Muslim used to be. You can visit CERN's public website and find a similar blank space where the metastability implications of the Higgs mass should be discussed and are not. And the funding for even the current program is collapsing. In early 2026, the United Kingdom Science and Technology Facilities Council announced 30% cuts to particle physics, nuclear physics, and astronomy. Mike Lockwood, the president of the Royal Astronomical Society, called it a catastrophe for science. In the United States, the 2026 federal budget proposes cutting collaboration with CERN entirely. Congressman Bill Foster, one of the only physicists serving in the US Congress, estimated total proposed cuts to fundamental research at more than $25 billion. Peter Jenny, former head of the Atlas experiment, said the American cuts would be shooting at their own feet. The connection between the nightmare scenario and the funding crisis is direct. As Science magazine reported, if the LHC finds nothing new, it will be harder to convince the governments of the world to build the next bigger, more expensive collider. The LHC found nothing new, and the governments are responding accordingly. The field that bet everything on finding new particles at the TeV scale is now facing the possibility that the public and its elected representatives will not fund the next roll of the dice. Natalie Wolchover, one of the best science journalists working today, wrote the definitive summary of this moment for Quantum magazine in March of 2022. Not only had the $10 billion proton smasher failed to answer a 40-year-old question, she wrote, but the very beliefs and strategies that had long guided particle physics could no longer be trusted. Read that sentence carefully. She is not saying the standard model failed. She is saying the methods used to extend it failed. The model survived. The field that built it is in crisis, and the machine that was supposed to resolve the crisis is running out of money. Isabel Garcia, a physicist at the Kavli Institute for Theoretical Physics at UC Santa Barbara, offered what might be the most honest assessment of where things stand. Some people call it a crisis, she said. That has a pessimistic vibe associated to it, and I do not feel that way about it. It is a time where I feel like we are onto something profound. She may be right. It is possible that the absence of new particles is itself a clue, that the fine-tuning of the Higgs mass and the cosmological constant are not problems to be solved, but features to be understood. But understanding them requires tools that do not yet exist, theories that have not yet been formulated, and increasingly funding that is being taken away. And here is where the cosmic ray argument enters the picture, because it is the argument that is supposed to make all of this irrelevant to the question of safety. The argument goes like this. Cosmic rays, high-energy particles from astrophysical sources, have been bombarding the Earth, the Moon, neutron stars, and every other object in the universe for billions of years. Some of those cosmic rays carry energies far beyond anything the LHC can produce. Ultra-high energy cosmic rays detected by experiments like the Pierre Auger Observatory have been measured at energies exceeding 10 to the 20 electron volts, which is millions of times higher than the LHC's beam energy. If particle collisions could trigger vacuum decay, cosmic rays would have done it already. They have been doing it for 13.8 billion years, hitting dense objects like neutron stars where the collision products cannot escape. The vacuum has not decayed, therefore the LHC cannot possibly be a risk. This argument is strong. It has been published in formal safety assessments by CERN's own advisory panels. It is cited in every discussion of vacuum decay and collider safety. And for the standard model's description of vacuum decay, it is essentially airtight. But the argument assumes that the standard model's description of vacuum decay is the only mechanism by which the vacuum could transition to a lower energy state. It assumes that bubble nucleation through quantum tunneling of the Higgs field, the Coleman-de Lucia instanton, is the complete picture. It assumes that no other field, no other coupling, No other pathway exists that could catalyze or trigger a transition in a way that the Standard Model does not describe. We have just spent most of this story establishing that the Standard Model is missing at least 95% of the universe's energy content, that it cannot account for dark matter, that it cannot generate neutrino masses without new fields, that the cosmological constant problem suggests something fundamental is wrong with how the theory handles vacuum energy, that the hierarchy problem points to unknown physics at or above the TV scale, that the strong CP problem demands either a new symmetry or a new particle that has not been found. If any of those missing pieces interact with the Higgs field, and most of them almost certainly do, then the Standard Model's description of vacuum decay is incomplete. The cosmic ray argument proves that the Standard Model's vacuum decay mechanism cannot be triggered by high-energy collisions. It does not prove that no vacuum decay mechanism can be triggered, because it does not account for mechanisms the Standard Model does not describe. To be more precise about what this means, the Standard Model contains one scalar field, the Higgs. Vacuum decay in the Standard Model proceeds through tunneling of this single field. The tunneling rate is the one calculated by Andreasen and collaborators. But many extensions of the Standard Model contain additional scalar fields, singlet extensions, two Higgs doublet models, the NMSSM, composite Higgs models, and others. In these models, the vacuum can decay through pathways that involve the additional scalars, and those pathways have different tunneling rates than the single Higgs calculation. In some cases, the additional scalars open faster channels. In others, they stabilize the vacuum completely. The cosmic ray argument guarantees safety for the decay modes that cosmic rays can probe, which is all of the single field modes. But if the true theory of nature contains additional scalars that couple to the Higgs, the vacuum dynamics could include modes that cosmic ray collisions do not necessarily trigger in the same way as collider collisions. The center of mass energy is not the only relevant parameter. The specific quantum numbers of the initial state, the coherence of the collision, the number of simultaneous interactions, all of these can differ between cosmic ray impacts and collider events. This is not the same as saying the LHC is dangerous. It is not. The overwhelming probability, based on everything we know and the billions of years of cosmic ray data, is that particle collisions at any achievable energy cannot trigger vacuum decay through any mechanism. But the honest version of the safety argument is more nuanced than the public version. The public version says the LHC is safe because cosmic rays prove it. The honest version says the LHC is safe according to every model we have, and the models we have are known to be incomplete in ways that specifically affect the vacuum stability calculation. The gap between those two statements is not large enough to justify alarm, but it is large enough to justify the question that this entire story has been building toward. If the model is known to be incomplete, and the vacuum is known to be metastable, and the lifetime calculation depends on the model being complete, and the safety argument depends on the model's description of decay being the only relevant one, then the certainty that everybody projects about this topic is not supported by the physics. What is supported by the physics is a very high probability of safety, bounded by a very large but not eliminable uncertainty that arises from the incompleteness of the theory itself. That is not a comfortable conclusion. It is not a headline. It is not a press release. It is the kind of conclusion that gets discussed in the technical appendices of safety reports and then summarized in the executive summary as safe. And for practical purposes, that summary is correct. But for purposes of understanding what CERN actually found when it measured the Higgs boson, and what that measurement actually means for the stability of the universe, the full picture matters. The full picture is that the Standard Model cracked open the question of vacuum stability by measuring the Higgs mass, produced 3 anomalies that might have pointed toward an answer, watched all 3 collapse, catalogued 7 permanent failures that it cannot fix, established that the vacuum is metastable with a lifetime that depends on unknown physics, ran the most energetic collisions in human history inside that metastable vacuum, and then faced the withdrawal of the funding that would allow the next generation of experiments to search for whatever lies beyond. And nobody is talking about it. Not in those terms. Not in a way that connects these pieces into the picture they actually form. The specialist coverage exists, buried in Quantum magazine articles and CERN Courier editorials, and Hossenfelder's YouTube channel. But the mainstream conversation, the one that reaches the public that funds these experiments through their taxes, tells a simpler story. A story about the Standard Model's triumph. A story about anomalies defeated and predictions confirmed. A story that is technically true and substantively misleading. Because the Standard Model did not triumph. It survived. And surviving a precision test is not the same as being the correct description of reality. Not when you are missing 95% of the universe. Not when your cosmological constant prediction is off by 120 orders of magnitude. Not when the vacuum you described as a shelf. The silence is the part of this story that should make you angriest. Not the metastability itself, because the physics is what it is, and being angry at the shape of the Higgs potential accomplishes nothing. Not the collapse of the anomalies, because experimental science is supposed to self-correct, and the fact that 3 promising signals turned out to be wrong is the system working as intended. Not even the nightmare scenario, because nature does not owe us supersymmetric particles, and the absence of new physics at the TeV scale is data. Not a failure. The silence. The gap between what the physics community knows and what the public has been told, that is the part worth being angry about. Consider how the story was reported. In July of 2012, the Higgs discovery was front-page news around the world. Rightly so. It was one of the great experimental achievements in human history, the culmination of 48 years of theoretical prediction and 16 years of accelerator construction and data collection. 4,000 physicists on Atlas, 3,000 on CMS, engineers, technicians, administrators, and governments across dozens of countries, all converging on a single measurement. The applause in the CERN auditorium was genuine. The tears in Peter Higgs's eyes were genuine. The pride was earned. But the metastability implication, which was established with high confidence by Degrassi and collaborators in a paper submitted the same month as the discovery announcement, received almost no mainstream coverage. The paper was published. It was cited hundreds of times within the specialist literature. It established at 98% confidence that the electroweak vacuum is not in its true ground state, and the general public, the people whose tax money built the machine, was told that the Standard Model had been confirmed and that the Higgs boson was the final piece of the puzzle. When the flavor anomalies collapsed in December 2022, the headline said, "Standard Model holds." When CMS contradicted the CDF W boson measurement in September 2024, the headline said, "Standard Model confirmed." When the Muon G-2 anomaly evaporated in June 2025, the headline said Standard Model survives again. Each headline was technically accurate. Each headline was also misleading in a specific and consequential way, because the narrative that emerged from those headlines was that physics is fine, the theory works, nothing to worry about, and that narrative is wrong. The Standard Model is not fine. It is the most precisely confirmed partial theory in science. It correctly describes roughly 5% of the universe's energy content and has nothing to say about the rest. Its greatest triumph, the Higgs discovery, confirmed that the vacuum is metastable. Its internal consistency requires fine-tuning at levels that range from 1 in 10 billion to 1 in 10 to the 32. Its predictions for the cosmological constant are off by 120 orders of magnitude, and the experimental anomalies that might have pointed toward a resolution have all disappeared, leaving the permanent failures as the only cracks in evidence. There is a word for a situation where the people who understand a problem best choose not to communicate it clearly to the people who fund their work. You can pick your own word, but whatever you call it, it describes the current state of science communication around the standard model and vacuum metastability with uncomfortable precision. This is not a conspiracy. Nobody sat in a room and decided to suppress the vacuum metastability findings. The mechanism is more mundane and more systemic than that. CERN's communications office produces press releases designed to sustain public support for a $20 billion research program. Press releases that say, "We confirmed the universe might be sitting on a metastable shelf," do not sustain public support. University press offices operate on the same incentives. Journals want citations, which means they reward positive results over null results, confirmations over confessions. Science journalists, the good ones, have written about the crisis in depth. Natalie Wolchova's work at Quanta has been exceptional. But Quanta magazine reaches physics enthusiasts. It does not reach the voting public. The result is a stratification of knowledge. At the top, theoretical physicists who understand the full picture, who know the vacuum is metastable, who know the lifetime depends on unknown physics, who know the standard model's failures are permanent and structural, and who discuss these things openly at conferences and in technical papers. In the middle, science journalists and popular communicators who report on individual anomalies as they rise and fall, but rarely connect them into the larger pattern. And at the bottom, the general public who have been told the Higgs was found, the standard model works, and physics is in good shape. That stratification is not neutral. It has consequences. When funding decisions are made based on public understanding of what physics has achieved and what it still needs to do, and the public understanding is that the standard model works and everything is fine, the funding decisions reflect that understanding. The United Kingdom cutting particle physics funding by 30% is not an irrational decision if you believe the standard model is complete and confirmed. It is a perfectly rational response to the story that has been communicated. The irony is that the same institutions now losing their funding are the ones whose communication strategies contributed to the misunderstanding. Sheldon Glashow and Steven Weinberg understood the standard model's limitations better than almost anyone alive because they built the electroweak piece of it. Their collaboration is one of the great intellectual partnerships in 20th century physics, and their falling out is one of its quieter tragedies. They were classmates at the Bronx High School of Science, graduating in 1950. They went to Cornell together, earned their bachelor's degrees in 1954. Glashow provided the algebraic framework for electroweak unification with his SU 2 times U1 gauge structure in 1961. Weinberg inserted the Higgs mechanism in his legendary 1967 paper, A Model of Leptons, 3 pages long, now cited over 18,000 times. Their friendship fractured over credit. Glashow recalled that Weinberg gave a talk in Tokyo that omitted Glashow's name from the historical development of the theory. "It was the issue which terminated our friendship," Glashow said in a 2020 interview with the American Institute of Physics. They spoke only rarely after that. The two men who built the theory that describes the electromagnetic and weak forces, the theory that is half of the standard model's electroweak sector, stopped talking to each other over a perceived slight at a conference. Weinberg died on July 23, 2021, in Austin, Texas, at age 88. Glashow's memorial statement captured the complexity with a precision that only decades of tangled history can produce. "Steve and I spoke only rarely since then," he wrote. "I regret that our long friendship and fruitful collaboration could not continue. Yet our lives had been so closely entwined that his death is not only a great loss for science, but also for me. There is something in that story that maps onto the larger narrative. Two people who built something extraordinary together, who understood its inner workings better than anyone else, who knew its strengths and its limitations intimately, and who could not continue to work together. The Standard Model is like that. Its creators understood it completely and could not agree on what it meant or where it should go. The theory is magnificent and incomplete, brilliant and broken, confirmed and wrong, all at the same time. And the people who know it best, the ones who built it and refined it and tested it, cannot agree on what to do about its failures. Some, like Glasgow, defend it fiercely. "I do like the Standard Model," he said. "I like it very much." Others, like Hossenfelder, attack the methods used to extend it. Still others, like Arkani-Hamed, argue that the crisis itself is a clue, that the fine-tuning is telling us something about the deep structure of physical law that we have not yet understood. And while they argue, the vacuum sits, metastable, patient, holding a configuration that the equations say is temporary. Peter Higgs died on April 8, 2024, at his home in Edinburgh. He was 94. He had never used the internet, never owned a mobile phone, never sent an email. He lived a quiet life in a city he loved, and when reporters occasionally found him, he told them the discovery had ruined his life. Because fame was not really Peter's style, he published fewer than 12 papers. He declined a knighthood. He learned about his own Nobel Prize from a former neighbor who spotted him on the street, because he had deliberately left his flat to avoid the media and had no phone for the committee to call. His particle, the one predicted in the extra paragraph of a paper that was initially rejected as having no relevance to physics, turned out to have a mass that places the entire universe on a ledge, 125.2 GeV, not 128, which would have meant stability, not 115, which would have meant clear instability, and a much shorter vacuum lifetime. 125.2, right in the metastable zone. 98% confidence, not even close to the boundary. The man who never wanted to be found made a prediction that revealed something about reality that cannot be unfound. And when he sat in that auditorium on July 4th, tears forming in his eyes, watching the data confirm his prediction, the number on the screen was simultaneously his vindication and the universe's confession. And Robert Brout, who independently proposed the same mechanism in 1964 with Francois Englert, died on May 3, 2011, 14 months before the discovery. The Nobel Prize cannot be awarded posthumously. Brout never knew that the particle existed. He never knew what its mass was. He never knew that his theory confirmed the vacuum is a shelf. Englert accepted the Nobel alongside Higgs in 2013, and the absence of the third name was felt by everyone in the room. The story of the Standard Model is, in many ways, a story about what people choose to see and what they choose to ignore. Higgs saw the mechanism. The editors of physics letters chose to ignore it. Salam saw the electroweak unification. Pakistan chose to erase him. The physics community chose to set those implications aside. The Higgs mass measurement confirmed metastability. The press releases chose to celebrate instead. And none of this changes the physics. The Higgs field does not care about press releases. It does not care about funding decisions. It does not care about the Glasgow-Weinberg feud, or the erasure of Salam, or the retirement of Hossenfelder's university affiliation. It sits at 246 GeV, permeating every point in the observable universe, maintaining the configuration that allows atoms to exist, and chemistry to function, and brains to think. And the math says that configuration is not the lowest energy state available. The true minimum is somewhere else. Deeper, different, incompatible with everything that currently exists. The lifetime calculations say we have time. 10 to the 133 years, more time than the concept of time can meaningfully describe. And those calculations depend on assumptions we know are wrong. Not suspect, not questionable, wrong. The standard model is missing fields. It is missing 95% of what exists, and the vacuum lifetime is a function of all of it. You cannot take the most precisely tested theory ever built, demonstrate that it fails in 7 specific and catastrophic ways, close every anomaly that might have pointed toward a fix, and then use that same theory's vacuum lifetime calculation as reassurance that everything is fine. Or rather, you can. Physicists do. But the reassurance carries an asterisk that the press releases omit. So where does that leave you? You clicked on this because the title said CERN found a crack in reality, and nobody is talking about it. That title was not clickbait. Everything in it is literally true, and the reality is worse than the title suggested, because the crack is not an anomaly, it is not a glitch in the data. It is not a statistical fluctuation that will resolve with more measurements. The crack is structural. It is built into the Higgs mass. It is built into the standard model's own equations. It has been confirmed by multiple independent groups at multiple levels of theoretical precision, and it says the same thing every time. The vacuum you exist in is not the ground state. It is a false minimum, a shelf on an energy landscape that continues downward. The 3 anomalies that generated the most excitement in the physics community over the past decade, the B-meson flavor anomalies, the CDF W boson mass measurement, and the Muon G-2 discrepancy, all pointed in promising directions. All suggested new particles, new forces, new physics that might explain the metastability, stabilize the vacuum, or at least tell us what lies beyond the standard model. All 3 collapsed. The flavor anomalies were a systematic error in particle identification. The W mass anomaly was an isolated measurement contradicted by every subsequent experiment. The Muon anomaly dissolved when theorists recalculated their prediction from lattice QCD. The escape routes closed, one by one, and the community was left exactly where it did not want to be, standing on the shelf with no map of what lies below and no ladder to climb to stable ground. The 7 structural failures of the standard model, the cosmological constant off by 120 orders of magnitude, the hierarchy problem requiring fine-tuning to 1 in 10 to the 32, the strong CP problem with no known solution, the matter-antimatter asymmetry 8 orders of magnitude too large, dark matter making up 1/4 of the universe with no candidate particle, neutrinos having mass when the theory predicts they should not, the Hubble tension at 5 sigma between the early and late universe. None of these are going to go away. They are not anomalies. They are features of a theory that is brilliant within its domain and silent outside it. And every one of them represents missing physics that, if discovered, would change the vacuum stability calculation in ways that nobody can currently predict. The machine at CERN continues to operate. Run 3 is producing data at 13.6 TeV, 280 inverse femtobarns delivered and counting. The proton beams cross 40 million times per second, producing roughly 40 collisions per crossing, and the detectors record everything. The standard model is confirmed with each new dataset. The nightmare scenario, the Higgs, and nothing else is the reality. And the proposals for the next generation of experiments, the future circular collider, at 100 TeV, are being developed at the same time that the governments funding current experiments are withdrawing support. There is a specific kind of vertigo that comes from understanding this situation clearly. It is not fear exactly. The probability that the vacuum will decay during your lifetime, or during the lifetime of the solar system, or during the lifetime of any structure currently observable in the universe, is so vanishingly small that worrying about it is not rational. The Andreasen calculation, even with its 2024 correction, gives a lifetime of 10 to the 133 years. Even if the unknown physics shorten that by 60 orders of magnitude, an absurdly dramatic change, the lifetime would still be 10 to the 73 years. incomprehensibly longer than any cosmological timescale. The vacuum is almost certainly safe in any practical sense. Almost. But almost certainly is not the same as certainly. And the difference between those two phrases is not semantic. It is the difference between a closed question and an open one. The closed version says the vacuum is stable, the LHC is safe, the standard model works, go back to sleep. The open version says the vacuum is metastable, the lifetime depends on physics we do not have. The model that gives us the reassuring number is the same model that is wrong about 120 orders of magnitude of vacuum energy. And the question of what happens if the unknown physics is relevant to the tunneling rate is genuinely unanswerable with current tools. The open version is correct. The closed version is what gets communicated. And the machine keeps running. Let me tell you what vacuum decay would actually look like in concrete physical terms if it happened. Not because it is going to happen. Almost certainly it is not. But because you deserve to understand what the math describes, and because the specificity of the physics is part of what makes the silence so difficult to justify. A bubble of true vacuum would nucleate at some random point in space-time, not because of a collision, not because of an external trigger, but through a spontaneous quantum tunneling event, the same kind of tunneling that allows radioactive atoms to decay and that allows the sun to fuse hydrogen. The bubble would begin microscopic, smaller than a proton, and would immediately begin expanding. The expansion would accelerate until the bubble wall reached a velocity indistinguishable from the speed of light. Inside the bubble, the Higgs field would sit at the true minimum of the potential, a value vastly different from 246 GeV. Every particle mass would change. The electron mass, the quark masses, the W and Z boson masses, the strong force coupling constant would change. The electromagnetic coupling constant would change. Chemistry would not work. Atoms would not be stable. Nuclear physics would be different. The specific values would depend on the location of the true minimum, which is not precisely known, but the general result is that no complex structure could exist. The bubble wall itself would carry enormous energy, roughly the energy density difference between the false and true vacuum, concentrated in a shell expanding at the speed of light. Ahead of the wall, the universe would appear completely normal until the instant the wall arrived. There would be no precursor signal, no gravitational wave, no burst of radiation, nothing. The speed of light is not just the speed limit for information, it is the speed limit for causation, and the bubble wall travels at that limit. The first photon that could possibly carry information about the bubble's existence would arrive at the same time as the bubble itself. Coleman and DeLucia worked out the gravitational corrections to this picture in 1980. With gravity included, the situation gets worse. In some parameter ranges, the bubble interior is not just a different vacuum, but a collapsing spacetime, a crunching region that contracts to a singularity. The structures capable of knowing joy that Coleman mentioned would not just be reconfigured, they would be gravitationally crushed. The interior of the bubble would not be a different universe. It would be no universe at all. The probability of this happening in any given cubic light year of space per year is absurdly small. The standard model calculation gives roughly 10 to the minus 582 per gigayear per cubic gigaparsec. That is a number so small that writing it as a decimal would require nearly 600 zeros after the decimal point before you reached the first non-zero digit. For all practical, physical, rational purposes, it is not going to happen. The vacuum you are sitting in right now is as safe as anything in physics can meaningfully be. But, and this is the last but, the one the entire story has been building toward. That number, 10 to the minus 582, is derived from the standard model, the complete standard model, with all its known fields and couplings, and nothing else. If there are additional scalar fields coupled to the Higgs, The tunneling rate changes. If there are hidden sectors that modify the potential at high field values, the tunneling rate changes. If the Higgs field is not fundamental but composite, the tunneling rate changes. If quantum gravity effects become relevant near the barrier, which some approaches to quantum gravity suggest they do, the tunneling rate changes. In some theoretical models, additional scalars can reduce the barrier height enough to shorten the vacuum lifetime by dozens or even hundreds of orders of magnitude. In others, they raise the barrier and stabilize the vacuum entirely. The direction of the effect depends on the specific new physics, and we do not know what the specific new physics is. So the calculation is not wrong. It is incomplete. It is the best answer available given the current state of knowledge, and it is overwhelmingly reassuring. But it carries an assumption that the physics community knows is false. The assumption that the standard model is the complete description of particle physics, and the magnitude of the error introduced by that assumption is unknown. Not small, not large, unknown. That is the crack. Not a crack in the data, a crack in the certainty. The measurements are solid. The Higgs mass is what it is. The quartic coupling crosses zero where the calculations say it crosses. The metastability is confirmed. What is not confirmed, and cannot be confirmed with current physics, is whether the metastability is as benign as the standard model says it is. The model that gives us the reassuring lifetime is the same model that fails to account for 95% of what exists. The same model whose vacuum energy prediction is off by 120 orders of magnitude. The same model that requires a fine-tuning of 1 in 10 to the 32 to produce the Higgs mass it measured. The same model whose 3 most promising anomalies all vanished, leaving no experimental guidance toward whatever comes next. And CERN turned the machine back on. Not because the risk is high. It is not. Not because the physicists are reckless. They are not. They are careful, rigorous people doing the best work they can with the tools they have. They turned it back on because the cosmic ray argument is persuasive, because the standard model calculation gives an enormous lifetime, because there is no evidence of any mechanism that could trigger decay through collisions, and because the alternative, shutting down the single most powerful tool humanity has ever built for probing the fundamental nature of reality, would be a capitulation to a fear that the available data does not support. All of that is reasonable, all of that is defensible, but none of it changes the underlying situation. The vacuum is metastable. The lifetime depends on unknown physics. The model that reassures us is the same model that confesses its own incompleteness in at least 7 quantifiable ways. And the people who understand this best discuss it in technical papers and conference talks, and then draft press releases that say the standard model has been confirmed once again. Peter Higgs never wanted to be famous. He wanted to understand the mechanism that gives particles mass. He succeeded, and his success revealed that the vacuum is a shelf. Abdus Salam wanted to unify the forces of nature. He succeeded, and his success was erased from his own tombstone. Sidney Coleman wanted to understand what happens when a false vacuum decays. He succeeded, and his conclusion was that it eliminates the possibility of anything capable of knowing joy. Sheldon Glashow and Steven Weinberg wanted to build the electroweak theory. They succeeded, and their friendship did not survive the achievement. Nima Arkani-Hamed wanted naturalness to guide physics to the next theory. It did not. He adapted, and the adaptation cost the field its most reliable compass. Every one of these people gave something to the standard model. Every one of them watched it produce consequences they did not intend and could not control. The model they built works. It works spectacularly well at everything it attempts to describe, and it fails spectacularly at everything it does not. The anomalies were false alarms. The real crisis was always the silence, the absence of any experimental guidance toward whatever comes next. What does this mean for you, concretely? It means that the ground state of reality, the thing you are made of, The vacuum that supports atoms and light and chemistry and thought is not the lowest available option. It means the equations that describe it have been checked at the highest precision modern mathematics allows, and they say the same thing every time. Metastable. Temporary on a timescale that vastly exceeds the age of the universe, but finite in a way that stable is not. It means the three experimental results that might have led physicists toward an understanding of what lies beyond the standard model, results that might have illuminated the full picture of vacuum stability, have all evaporated. It means the 7 structural failures of the model that gives us the reassuring vacuum lifetime are quantified, published, and unresolved. It means the funding to search for answers is being cut, and it means the public narrative, the one you encounter in headlines and press releases and popular science videos, systematically omits the connection between these facts. You are not in danger. Let that be clear. The physics does not support panic, and anyone who tells you the LHC might destroy the universe is not reading the same papers the physicists are reading. The cosmic ray argument is strong. The lifetime calculation is enormous. The probability of decay is negligible on any timescale that has meaning for you or your species or your planet. But you were never told the full story. You were told the Higgs confirmed the standard model. You were not told the Higgs confirmed the vacuum is a shelf. You were told the anomalies collapsed and the model survived. You were not told the collapses closed every experimental pathway toward understanding the metastability. You were told the standard model is the most successful theory in science. You were not told it cannot account for 95% of what exists, and that this gap affects the very calculation meant to reassure you. That gap between what you were told and what the physics says is the crack. Not in reality itself, though the metastability is real. The crack is in the communication, in the institutional habit of presenting a partial picture as a complete one. In the press releases that say confirmed, when the technical papers say confirmed, but incomplete. In the silence where honest, clear public discussion of the vacuum metastability and its dependence on unknown physics should be. That silence after 500 inverse femtobarns of the highest energy collisions ever produced on Earth, after $10 billion and 4 decades of work, after every supersymmetric particle excluded and every Higgs coupling confirmed to be exactly what the standard model predicted, is now the loudest thing in physics. The Higgs field sits at 246 GeV. It has been sitting there for 13.8 billion years. The equations say it is not in the lowest state. The equations say a lower state exists. The equations say the transition between states would propagate at the speed of light, rewriting the laws of physics as it moves, eliminating everything you know and replacing it with something you would not recognize as a universe. The equations say the probability of this happening is vanishingly small. And the equations that say the probability is vanishingly small are the same equations that cannot account for 26.5% of the universe's mass, cannot explain why space has the energy density it has, and cannot tell you why the Higgs mass is what it is. The calculations have been checked. The Higgs mass is 125.2 GeV. The top quark mass is 172.52 GeV. The quartic coupling crosses 0 at 10 to the 10 GeV. The barrier peaks and the landscape drops. Somewhere on that landscape, below where we sit, the true minimum waits. It has been waiting for longer than the universe has existed, and whether it will wait forever depends on physics that the smartest people alive cannot currently describe. You were never told this, not because it is not true, but because truth, when it is this uncomfortable, tends to get published in journals and discussed at conferences and left out of the press releases. The crack in reality is not a metaphor. It is a measurement, and the silence around it is not an oversight. It is the sound of a question that the people who should be answering it cannot answer yet. and every 40 millionths of a second, beneath the French-Swiss border, two beams of protons cross. Again and again.